Hello, this is Mrs. Huntley. We are in Module 5, Lesson 3, Linear Functions and Proportionality. You should be on page 18 of your module, and your essential question for this lesson is, what is a linear function? Hopefully you remember that in Lesson 2, we defined function as the purpose of a function is to be predictive, meaning that we can make predictions based on the relationships between x and y. And a function is a rule or a formula that assigns each input to exactly one output. So we're going to be looking at linear functions. Now we spent a whole module on linear equations, and we learned what the word linear means, and hopefully you're recognizing the word line in linear. When something is linear, when we graph it, the graph is going to be a straight line. So let's look at example 1. Example 1 should look familiar. We've had several problems like example 1. I think they were on some assessments, they were on some homework assignments. This is not new. Maybe having a table that's flat instead of going up and down with our x's on the left and our y's on the right, that might be new. But for the most part, we've seen problems like this before. So let's take a look at this and see if we can determine, first of all, if it's a function, and secondly, whether it's linear. So functions, each input, we have to check our inputs, see if they're all unique. And if two inputs are the same, we need to check the outputs to see if they're also the same, or if we have an input that's assigned to two different outputs. So let's just check our inputs really quick. Our inputs are our x's. So really quick scan through our x's here, and they are all unique, 1 through 8. We don't have any repeat numbers. So I'm going to say right now it's a function. We don't know if it's linear yet, but we know it's a function. So to check to see if it's a linear function, we need to see how our rate of change is changing at each interval. So our x's are going up by 1 each time. One plus 1 is 2, 2 plus 1 is 3, and so on. Our y's, 125 to get to 250, that's going up by 1.25. 250 to get to 375, okay, that's also going up by 1.25. 375 to $5, 1.25. And $5 plus 1.25. Okay, so it looks like, let me just check these last couple because it could fool you at the end. 25. Okay, each of our intervals, each additional bag of candy costs another $1.25. So I'm going to say, yes, this is a linear function. Let's define it first. A linear function is a function with a linear relationship. Again, linear relationship simply means when you graph it, it's going to be a straight line. It means that the rate of change is constant between all the x and y values. The graph of a linear function is going to be a straight line. How do you know? How do you identify a linear function in table form? Check the rate of change. The rate of change should be constant throughout the whole table. How do you identify a graph of a linear function? It's going to be a straight line. Okay, so if we're graphing the table of the data, or graph the table data, that, I don't know why that was difficult for me to say, but it was. If we don't buy any bags of candy, it's not going to cost us any money. If we buy one bag of candy, I should label this. This should be labeled. Bags of candy. And this is cost. Your x and your y axis should always be labeled with what's going up and what's going across. So if I buy one bag of candy, it's going to be $1.25, be about there. 2 bags of candy is going to be $2.50, so halfway between. 3 bags of candy, $3.75, so almost 4. 4 bags of candy is going to be 5. 5 bags of candy is $6.25. 6 bags of candy is $7.50. 7 bags of candy is $8.75. and 8 bags of candy will be $10. So when I use a straight edge and connect these lines, it should all be on a straight line. And it is. It looks like some of the points are off a little bit, but that's because I wasn't being exactly precise with my half measurements, but it is going up in a straight line. So next they're asking what equation or rule describes the function. So y is going to be our total cost. Oopsie. X is the number of bags of candy. Our rate of change, or our slope, is 1.25. So putting this into slope-intercept form should be easy. Y equals 1.25x. I could say plus 0, but I don't have to. Would it make sense for x to ever be a negative number? Let's think about this. What is x representing? The number of bags of candy. Can I buy negative bags of candy? No, I cannot buy a negative bag of candy. So it does not make sense that x would ever be negative. Would you say the table represents all possible inputs and outputs? Let's think about this. Let me go back to the table. 1 through 8. Would it be possible for me to buy 0 bags of candy? Sure. Would it be possible for me to buy more than 8 bags of candy? Sure. So no, I'm going to say no, the table doesn't represent all possible inputs and outputs. I could definitely buy more than 8 bags of candy. Okay, our second example. Walter walks 8 miles in 2 hours. What is his average speed? So to get his average speed, we're going to take the miles that he walks divided by the time that he's walking. So 8 divided by 2 would be 4, a whole number 4, or 4 over 1, which means he walks 4 miles per hour. That's his average if he walks 8 miles in 2 hours. Now we can assume that he's going to be walking at a constant rate, meaning that his average is going to be the same over an extended period of time. So it says describe the function in this example. We're going to say the distance. Let me type here because I didn't get this prepared ahead of time. I'm not sure exactly why. Probably because I'm still coming back from spring break as well. So describing the function, the distance Walter walks is a function of the time he spends walking. So the output, the distance that he goes, is dependent upon the amount of time he spends walking. What limitations do we have to place on x? Let's think about this. Can he walk for a negative amount of time? No. So x cannot be negative. And if I'm representing that with symbols, I would say x has to be greater than or equal to 0. That's how I would represent this. Let's see. If I wanted to write an equation that would represent this function, I could write an equation. Y would be my total distance, x is going to be my time, and my rate of change is 4 miles per hour. So I would say y equals 4x. And at 0 time, he's gone 0 distance. Hopefully, this is not like messing you up, or you might even be thinking, okay, we've done this before. I'm not understanding why we have a new lesson and we're calling it something different. We're looking at tables that are flat instead of upright. A linear function is described by a linear equation. So those of you that understood linear equations, this should be pretty straightforward, pretty easy. The thing is figuring out whether it is linear or not, and that's comparing your changes in y over your changes in x, looking at graphs, determining whether they're straight line, that type of thing. Again, nothing new, maybe just some new language surrounding it. So example 3, Veronica runs at a constant speed. The distance she runs is a function of the time she spends running. So that's again how you describe your function. The function has the table of values shown. It says below, but it's actually to the right. And again, it's one of those flat tables. So our time is our x, our distance is our y, time is on top, distance is on the bottom. So if we're trying to determine whether this is a linear function or not, we can look at our change in y and put that over our change in x. So change in y, we're going plus 1, plus 1, plus 1. Change in x, we're going plus 8, plus 8, plus 8. So it's going to be change in y is 1 over 8. So what rule or equation describes the function? Again, y is our total distance, and x is our time. Okay, so y is the total distance. Veronica can run in any time, any x time interval. Using words describe the function. They kind of already did, but we'll go ahead and do it again. Oh, sorry about that. The rate of change or slope means that she can run 1 mile in 8 minutes. So hopefully we're making some connections with that. The distance that Veronica can run is a function of the number of minutes she is running. And it was kind of over here too. The distance she runs is a function of the time she spends running. I said the number of minutes she spends running because that's just how it made sense to me. And this, what the rate of change means, that is important. I want you to make sure that you're understanding the context of what you're doing. So this is 1 mile in 8 minutes. 1 is your distance, so it's always distance over time. Remember, we've been saying distance over time for what, 2 modules now. What limitations do we need to place on x? Okay, can Veronica run negative minutes? No, she can't. She can't run negative miles. She can't run negative minutes. So our x has to be greater than or equal to 0. The word limitations, that becomes important as we get into more complex functions. Right now you're probably thinking, well, it's very straightforward as far as that goes. I know you can't run negative minutes. Well, what happens if you can do something for a negative amount of time, or if there is something that can be done in a negative way? So those will be coming in our future. Example 4. Let's take a look here at what we've got going. Yeah, we can do this. Example 4. Water flows from a faucet at a constant rate. That is, the volume of water that flows out of the faucet is the same over any given time interval. If 7 gallons of water flow from the faucet every 2 minutes, determine the rule that describes the volume function of the faucet. So y is going to be the volume of water that flows. X is the number of minutes that the water is flowing. The amount of water that flows is a function of the time that the faucet is running. So if we're trying to figure out our rate of change here, or the rate that it's coming out, we've put gallons over time. So this would be 7. Come on, pen. 7 over 2. Or we can say that's 3.5. Gallons per minute. If we're writing an equation, it's going to be y equals 3.5x. And again, none of this is new. Hopefully it's not confusing. Now this next part might be a little bit confusing. Assume that the faucet is, not if, assume that the faucet is filling a bathtub that can hold 50 gallons of water. So our y, we know, is 50. So it'd be 50 equals 3.5x. If we want to solve for how long it's taking, we're going to divide both sides by 3.5, and x is going to be approximately 14.2857 and goes on from there. So we're going to say about 14 minutes to fill the 50-gallon tub. Okay. Now assume that you're filling the same tub with 50 gallons with the same faucet where the water is flowing at 3.5 gallons per minute, but this time the tub already has 8 gallons in it. Will it still take 14 minutes to fill the tub? No, it's not, because we've already got some water in there. So let's set this up. How would we do it? We're still looking for 50 as our total. 50 is our total, equals 3.5x. But now we add in what's already in the tub. So we're going to subtract 8 from both sides. So we'll have 442 equals 3.5x. Divide both sides by 3.5, and we get x equals 12. So it will take 12 minutes if there's already 8 gallons in the tub. So it says generate a table of values for this function. So at 0 minutes, we already had 8 gallons in the tub, right? At 3 minutes, we take our 3 and we plug it into the equation. So y equals 3.5 times 3 plus 8. So 3.5 times 3 plus 8 is 18.5. Same thing with the next one. Y equals 3.5 times 6 plus 8. It's going to be 29. 3.5 times 9 plus 8, and y equals 3.5 times 12 plus 8. What I'd like you to do is come up with the values for the last two on this table and bring it to class tomorrow completed. We will do example 5 and the on your own exercises tomorrow in class, as well as the independent practice. I will be assigning the summary, so keep in mind a linear function can be described by a rule in the form y equals mx plus b, where m and b are the constants. M is your rate of change and b is your initial value. Constant rates and proportional relationships can be described as linear functions where the rule is a linear equation. There is the bell, so I have to wrap it up here. I will see you in class tomorrow.